if you cut or rotate it by the angle of phi, I'm asking for these two. So what you can do, just change phi to phi plus 90, because this plane it has 90 degrees offset from this one. So just plug in the new angles with the phi plus 90, you will get the correct value. All right. We are on failure theory. So, just to refresh, we have two types of the material, ductile and brittle material. For static failure, depending on what type of material we have, we are going to use different failure theories. For ductile material, we are using these three failure theories: maximum shear stress that we talked about that on last Thursday class, distortion energy, and ductile Coulomb theory. If you remember, when we talked about properties of material, for most of ductile material, Sy for tensile strength is going to be equal to the Sy for the compressive strength for most of the ductile material. But there are some ductile materials where Syt is not equal to Syc. So for these types of the material, we have to use DCM theory. So we cannot use the first two. So for all ductile material, you can use DCM, but for the materials which they have Syt different than Syc, you have to use DCM. And you will see the failure theories for brittle material. We will go over each failure theories one by one. We already covered maximum shear stress theory. So this theory says the failure occurs when the maximum shear stress it equals Sy divided by 2. We call it failure criteria. So the failure occurs when the maximum shear stress on the component is going to be equal to Sy2. We can say Sy2 is going to be Sy, which is shear yield strength. If you want to define the yield strength for the shear, it's going to be Sy divided by 2, and Sy is the yield strength. And if I ask you what would be the maximum shear stress, it's always equals to sigma 1 minus sigma 3 divided by 2. If you want to incorporate the factor of safety instead of using this, we should use this, SSY divided by N, or SY divided by 2N. If you want to incorporate the factor of safety, N is factor of safety. If you want to calculate factor of safety, the factor of safety is going to be SSY divided by tau max, or SY divided by 2 tau max. So these are what you need to know about this theory. So if you are solving for factor of safety, we are using this. If you incorporate the factor of safety, you have to use that equation, which are the same. So tau max is sigma 1 minus sigma 3 divided by 2. We can cancel out these two, and after this equation. So now let's look at the failure criteria where we have different situations. Suppose we have plane stress element. We have plane stress elements. So you can find the Moore circle by using the Moore circle or stress transformation equation. You will find sigma A and sigma B, the principal normal stresses. If sigma A and sigma B both are positive, and assuming sigma A is greater than sigma B, what would be the failure criteria based on maximum shear stress theory? Is the question clear? I'm asking you to derive the failure criteria, which is this equals to SY2. Not working.
You right there?
Number 17.
That's the first.
Okay.
So shouldn't it be set SY over 2 equals to sigma 1 minus sigma 3 over 2?
Okay, yes.
And so sigma A would be sigma 1, and 0 would So over 2, set that equal to sy over 2. Multiply over the s2, so sy equals sigma a.
Sigma y. Sy. So, as Austin said, sigma 1, we are looking for this. Set sigma 1 minus sigma 3 divided by 2 equals to sy divided by 2. Sigma 1 is the greatest, sigma 3 is the smallest value. So the greatest is going to be sigma a, and 0 is going to be sigma 3. So sigma a minus 0 dividing by 2, it's going to be sy divided by 2. So we can cancel out these two. Sigma a equals to sy. So this is the failure criteria when both are positive. Sigma a and sigma b both are positive. So if I divide the plane to 4 quadrants, and this axis is representing sigma a, this axis is representing sigma b. If both are positive, means we are on the first quadrant. And if this is sy, if I ask you to draw this line, sigma a equals to sy, it's gonna be this line. Sigma a equals to sy. So this is gonna be this line. Now, if I move to the to the fourth quadrant, where sigma a is positive, but sigma b is negative. Sigma a is positive, but sigma b is negative. Apply the same thing. Sigma a is gonna be the greatest. It's gonna be sigma 1. Sigma 3 is gonna be the smallest one. So it's gonna look like sigma a minus sigma b divided by 2 equals to sy divided by 2. Or sigma a minus sigma b equals to sy. The failure criteria is gonna look like this. At sigma b equals to 0, if sigma b equals to 0, set sigma b equals to 0, sigma a should be sy. So pick that point. Sigma a equals to sy, and sigma b equals to 0. It's going to be this point. Now plug in sigma a equals to 0. At sigma a equals to 0, 0 minus sigma b is going to be sy. Sigma b is going to be negative sy. So the second point is going to be sigma b equals to negative sy, and sigma a equals to 0. This point. Now, since it's a linear function, just connect these two. You will get something like this. Make sense? Now I go to the third quadrant. If sigma a and sigma b both are negative, both are negative. and sigma B is gonna be less than sigma A. So then sigma 1 is gonna be 0, sigma 3 is gonna be sigma B, it's negative. So this equation is gonna change to 0 minus sigma B divided by 2 equals to Sy divided by 2. Or negative sigma B equals to Sy, or sigma B equals to negative Sy. If I want to draw that line, it's gonna be this one. So in all three cases, sigma A is greater than sigma B. So if we have vice versa, if sigma B is greater than sigma A, what I need to do, I just need to draw this line, draw this line, and draw this line. I'm gonna end up to this shape. If I assume sigma B is greater than sigma A. I don't show the process because we have symmetry, so we are gonna have the same lines. So this is the failure criteria for maximum shear stress theory. Any point inside this zone, it's gonna be the safe. And any point out of this zone, we are gonna see the failure. So this is how the maximum shear stress theory it's gonna work. You will see here case 1, this line, case 2, this line, and case 3 is gonna be this line. This line, and the other one, due to the symmetry, we can draw them. And inside the envelope, we are gonna have the safe stuff. So if you are given with sigma A and sigma B, suppose sigma A and sigma B is going to give you this point, sigma A, sigma B. So based on the loads applied to the component, the value of the sigma A and sigma B are given, and it's going to be at point A. So if you connect this point to the origin and continue, we call this load line. We call this line as a load line. So if you extend this line, it's gonna hit this vertical line at point B. So we can prove that factor of safety, it's gonna be equals to OB divided by OA. If we calculate that. So the load line, we are going to use this later, but this is the application of load line. It's going to help us to find the factor of safety if you don't want to deal with these equations. So graphically, if I ask you to find the factor of safety, you can just measure this, divided by this, it's going to be the factor of safety. But if you want to work with the equations, this is how you can find the factor of safety. Make sense? All right. Let's work on this class activity. Sigma A and sigma B are given, and the yield strength has been provided. So find the factor of safety based on maximum shear stress theory. Number 16, I don't think is there. Number 19, just got the course.
Can I try? But I think I got one.
Number 18. What should we do? I mean, I'm not looking for the final answer. What I'm asking you to, I just want to see your approach, and if there is any difficulty you will see at the class, then we can talk about that. So how can we find the factor of safety if the principal normal stresses of a plane stress is going to look like this? No, okay. Number 2.
No.
What do you think?
Five.
Pardon?
5.
How did you come out with
I did.
You just did. Okay. Number 23. What you need to do is finding, just look at the factor of safety. The factor of safety is defined as Sy divided by 2 tau max. Sy is the yield strength of the material which is given. So you need to find what would be the maximum shear stress, which always is sigma 1 minus sigma 3. On plane stress elements, we have sigma A, sigma B, and 0. Just rank them. Sigma A is the greatest, so sigma 1 is sigma A. Sigma 2 is the middle one, which is 0, and sigma 3 is negative 31.62. So means tau max is 31.62 minus 31.62 divided by 2, which is going to be 31.62 megapascal. N would be Sy, which is 70, divided by 2 times 31.62, or 35 divided by 31.62. It's greater than 1, so we are going to be safe and design. If you would like to show graphically, Sy is 70, this one is negative 70. Positive 31 is going to be somewhere here. Negative 31 is going to be somewhere here. So this point is going to be the point of the load. Sigma A and sigma B. If you connect this and extend, you will find point B. So this 35 divided by 31.62 is going to be OB over OA. So graphically and numerically, we can find the factor of safety. Yeah. Any question on this? What is the factor of safety? Means factor of safety. It's gonna be N. Yes, I mean, which is basically equals to that. All right, let's look at this one was theory, so we should compare with the experimental data. So the dots that you can see are the points coming from experimental data and the points which we have failure on them. So we did the test, experimental test with the different loading, and we could find the different points for the failure. As you see, all of the failure points are out of this zone. So it's telling me that our theory is conservative, and we can be safe if we use it for real design, because we expected to have failure if the points are out of the zone, which is the which can be matched with the experimental data. So I will keep this theory to be applied on the design. So we are keeping this because of this graph. The second theory that we would like to talk for ductile material is distortion energy theory, or DET. It's very simple theory. We don't go in details of the theory, we just introduce that. Based on this theory, we define one misses stress. One misses stress that I label with sigma prime. Sigma prime is defined as sigma 1 minus sigma 3 square, sigma 1 minus sigma 2, it doesn't matter. Sigma 2 minus sigma 3 square plus sigma 1 minus sigma 3 square square root divided by square root of 2. I just defined a new term and I name it as a one misses. So I define this as a one misses stress. How can I calculate the one misses stress? Just find the principal normal stress as sigma 1, sigma 2, and sigma 3. Plug in there and find the value for sigma prime, which is one misses. Then this theory says the failure theory is gonna look like this. When sigma prime or one misses stress is equals to yield strength, we are gonna have failure. So the failure criteria is gonna look like this. If you want to define the factor of safety, it's gonna be Sy dividing by sigma prime, which is the one misses. If you want to incorporate factor of safety, then you can say sigma prime should be equal to Sy divided by n. And that's all about this theory. You will find one single value, and once you have one single value, you can compare it with the single yield strength and decide about the failure. Make sense? So now on the next slide, I would like to talk about the different form of von Mises stress. So let's look at if you have plane stress. Equation 512 is gonna be this. You just see 2 inside the bracket. If you move these 2 inside the bracket, I can remove the square root. So if you have plane stress, it means we have sigma A, sigma B, and 0. I don't know which one is sigma 1, sigma 2, sigma 3, but one of them is going to be 0. So if this is the case, suppose sigma 2 is 0 or sigma 1 equals to 0. If I plug in one of the terms 0 here, I will end up to this equation for plane stress. Sigma prime is going to be sigma A square minus sigma A, sigma B, plus sigma B square for plane stress. How did I get this? Just suppose sigma 1 is sigma A, sigma 2 is 0. Just plug in sigma 1, sigma A, sigma 2 equals to 0. Sigma 2 equals to 0, sigma 3 is sigma B. If you do that and simplify von Mises stress, you are going to end up to this. Equation 514. If you don't like to find the principal normal stresses and you are given with the general stress elements, where we have sigma x, tau xy, tau xz, sigma z, sigma y, tau yz, tau yx. If we have this 6 term, then that equation is gonna change to this one. So again, you don't need to find the principal normal stresses if you are given with this value. You will end up with the same value for the von Mises stress. And if we have plane stress elements with no stress on this plane, then it's gonna change to this one. Any question about this? So as I said, this is how we can introduce the factor of safety by dividing S by N. And how can we calculate N? Just divide Sy by von Mises stress. So the key point in this theory is finding the von Mises stress. So let's do one class activity. Suppose we have a plane stress element like this with the pure shear. Based on the distortion energy theory, find the failure criteria for this one. What I'm asking is find the maximum allowable shear stress. What would be the maximum shear stress that I can apply for this to avoid the failure based on the distortion energy theory? Is that clear? Let me go to the class activity. It has the information that you need. These were questions that I have.
That also
Yep, that was close. I guess times 2. Before you roll over.
Notice I said you be doing something. Oh yeah, there's a quick.
That's 42.
Okay. I assumed the normal stresses were all 0, so I got 3 tau xy squared to the 1/2.
3 tau xy.
Yep.
So just look at this planar stress element. Sigma x is 0. We are not given with sigma a and sigma b. We can't find that, but it's easier to use this equation. This term is gone. This term is gone. We don't have sigma y. So we only have 3 tau squared. So 3 tau squared, s square root is going to be s square root of 3 times tau xy. I set it equals to sy, which is the failure criteria. So the maximum shear stress that you are allowed is sy divided by s square root of 3. So tau max .707 sy based on distortion energy theory. 1 over s square root of 3 is 0.707. So if I ask you to use the maximum shear stress theory, you end up tau max allowable is sy divided by 2 based on maximum shear stress theory. Tau max equals to, suppose n is 1, sy divided by 2. So the left side is going to be tau max. So the maximum allowable shear stress is 0.5 times sy. As you see based on the distortion energy theory, you can have, you are allowable to have greater shear stress than the maximum shear stress theory. So it means this theory is less conservative than maximum shear stress theory. So if tau max, for example, is 0.6 SY, 0.6 times SY. Based on distortion energy theory, since 0.6 is less than 0.707 times SY, you should be safe. But it's greater than 0.5 SY, you have failure. So this is what we can say about comparing this to this. All right, we continue tomorrow.